Hi everybody, so we are in chapter 8 now. We're talking about the concept of a confidence interval. So a confidence interval, this is what we're going to be talking about the next couple sections, but it also is going to keep coming up throughout the rest of the course as we start doing more of the hypothesis testing and more of the stuff we're going to see later on. So this is an important concept for us to talk about now that we're going to be using again later. So a confidence interval is a type of estimate, like one we've been seeing, but it gives us a particular level of confidence in our values, our answers. So when we talk about our level of confidence, we can say that, I am 90% confident that a particular value is within this interval, or I'm, 95% confident that this particular value lies in this interval. Generally speaking, we won't have 100% confidence in anything. That's just kind of how it works in statistics. But let's look a little more closely at what it means to have a confidence interval. So, first up, we need to just briefly talk about a point estimate. So a point estimate, So a point estimate is the value of a statistic that estimates the value of a parameter. So a parameter, if you recall, the difference between a parameter and a statistic. So a statistic goes with a sample, and a parameter goes with a population. Okay. So in this case, what we're doing is we are looking at trying to get an estimate or an approximate value for a population, because we don't necessarily know the value for the entire population. So the confidence interval tells us how confident are we that our answer is close enough. That's kind of what we're looking at here. So a confidence interval for an unknown parameter consists of an intervals of numbers based on a point estimate. So the level of confidence represents the expected proportion of intervals that will contain the parameter if a large number of different samples is obtained, and then this is how we find our confidence interval. So all of that just to kind of say, based on our point estimate, so our approximation based on a sample, how close do we think that is? How confident are we that our actual population value is going to be within a certain range of that? Okay, so when we're looking to find the confidence interval, we're going to take that point estimate minus the margin of error to get our lower bound, and the point estimate plus the margin of error to get the upper bound. Okay. So for this first example down here, just kind of setting it up. So a marketing department of an entertainment company is interested in the mean number of songs a consumer downloads per month from iTunes. Even though the population mean is unknown, we know that the population standard deviation, sigma, is 1 for a sample size of 100. What is the standard deviation for the sample mean? So if you remember the sample mean, that was x bar. We saw that in the last chapter. Okay, so x bar. So the standard deviation for the sample mean, so if you recall, that one was sigma over the square root of n, where n is the sample size. So that's going to be 1 over square root of 100, or 1/10, or 0.1 as a decimal. Okay. So we're going to use that here. So in this example, say the sample produced a sample mean of x bar equals 2. Find the 95% confidence interval for the population mean and interpret in context of downloaded songs from iTunes. So the first thing we need to do before we actually look at finding this confidence interval, I want to just come down here for a second to this note. We talked about this at the end of the last chapter, just this notation of z sub alpha. This is the z-score such that the area under the standard normal curve to the right of z sub alpha is alpha. So we have z sub alpha, this area to the right is alpha. Okay. Now we saw that in the previous chapter, but if you go back to the last page and look again at our definition for a confidence interval, the confidence interval is having a 1 minus alpha times 100% level of confidence. Okay, so if we say that we want 90% confidence, then we're saying the alpha value represents 10%, or 0.10. If we say we want 95% confidence, then the alpha value is what's left. Okay, it's 0.05, right, 5%. So that 1 minus alpha gives us that level of confidence. Okay? Now, in order to find the value that we want, so let me draw a normal curve here. Okay. So if we're, in this case, we're looking for a 95% confidence interval. So we're going to have our mean, right? Our population mean is there. And we're trying to find, with 95% confidence, an interval where that population mean should lie. So we don't know exactly where, but it's going to be somewhere in here. Okay. So that means that this area in here, that's going to be 0.95, right? Because that's 95%. So if that's 95%, then if you look at these areas out here on the tails, these two areas, if the middle is 95%, the two tails must be 5%. Right? So they're 5% together. But if we look at them separately and split them, then each of them is going to have half of that, right? Half of 5%, which would be 2.5%. So that would be 0.025 split. Okay, so that means that this tail has 0.025 of the area in it, and this tail has 0.025 of the area in it as well. So in order to find our 95% confidence interval, okay, so 95%, this corresponds to an alpha value of 0.05. Okay, because we have, again, so it's 1 minus alpha times 100%. So if that's 95%, then that's 1 minus 0.05, right, times 100%. So that's 0.95 times 100%, which is 95%. All right, so you can go about that way, finding the alpha value. Okay, but if you just remember that it's whatever's left, right, after we have the 95. So that's our alpha value. Now, in order to find the confidence interval, okay, so let me separate this off here. So for our confidence interval, we're going to need the upper bound and the lower bound. Okay, so what we're going to do to get these bounds is, for the upper bound, we take x bar, so that point estimate, plus z sub alpha over 2 times sigma sub x bar. So we're going to take our sample mean, right, that point estimate for the mean, plus z sub alpha over 2. And if you're wondering where that comes from, well then come back over to here, where we're taking the alpha value and splitting it into the two tails. So that means that this z-score right here, that's z sub alpha over 2. And this z-score down here, that would be negative z sub alpha over 2. Sub alpha over 2. Okay. So for the lower bound, we would take the mean, the point estimate, and then subtract z sub alpha over 2 times sigma sub x bar. Okay. So, in order to figure out these values, well, we already know x bar. That was given to us in the problem. We found the standard deviation in the last example. So this is going to be, so our confidence interval is going to be 2 plus or minus. Now when I write 2 plus or minus, so in case you haven't encountered this symbol before, this one just encompasses both of these cases. That way you don't have to write it twice, because everything's going to be the same except the plus and the minus. So basically all I'm doing is saying, well, one of my cases will be 2 plus this number, and the other case will be 2 minus this number. But we can just write it a little bit faster by combining it. Okay, and then plus or minus z sub alpha over 2, we'll come back to that in a second, and then times 0.1 was our standard deviation. Now, for z sub alpha over 2, so what we need to figure out is this value right here. Now we can do this, and we're going to do it using Desmos. In order to figure out what this is, we need to take the inverse CDF, right, of our normal curve, and we're going to do that. But in order to do that, we need to take the area as being everything to the left of this value, including this lower tail down here. And that's just how we find it using the technology. So z sub alpha over 2 is going to include all 95% here and the 0.025 here. So z sub alpha over 2, let's do this down here, z sub alpha over 2, this is going to be z, oops, let's see, alpha was 0.05 over 2, so z sub 0.025. Okay. So let's go ahead and find this on Desmos. Okay, so what we need to do is first create our normal function. So we go to functions, distribution, normal distribution. So let's just make it the standard normal, so 0 to 1, or mean of 0, standard deviation of 1. And then dot, inverse CDF. And then we need to put that decimal value of everything to the left of that z-score. So in this case, that's going to be the 0.95 plus the 0.0275. So that's 0.975. Okay, and then we'll go ahead and round that to 2 decimal places. So that'll give us 1.96 for our z-score. So this is 1.96. So I'll just put that in the equation here. So that's 1.96. All right. So what we got here is our set of equations. So 2 plus or minus 1.96 times 0.1. So our confidence interval, let's type it right here. Okay, so our 95% confidence interval is going to be the lower bound, if you run that calculation, is 1.804, and the upper bound is 2.196. Okay, so what does this interval tell us? So again, remember we are interpreting this in the context of downloaded songs from iTunes. So we had a sample mean of 2, and we were trying to determine a 95% confidence interval for the population mean of this value. So this tells us we are 95% confident that the mean number of songs downloaded is between those two numbers, so between 1.804 and 2.196. There we go. Alright, so again, that 95%, we're not interpreting that as a probability in this context. We're looking at it as just a confidence level. So how confident are we that the actual mean number of songs downloaded is between those two numbers? Well, we're 95% confident. So there is a 5% chance that we're wrong, but then you kind of have to ask yourself, well, how willing am I to be wrong? And generally we would say a 5% chance of being wrong versus a 95% chance of being correct, or confidence level of being correct, then that might be worth it. Okay. So, now suppose we have a level of confidence of 99%. So in this case, here's our curve, with our mean value in the middle here, and now we're heading way out to the outskirts here, because we're looking at this area in the middle encompassing 99% of the area, which means that the tails have to split that remaining 1%. Right? So the tails have to, so tails split 0.01. So cut that in half, that's 0.005 in both of the tails. So that's half a percentage in each of those tails. Okay. So our z-score here, okay, so z sub alpha over 2, in this case, alpha is 0.01, and then over 2, so that's z sub 0.005. Okay, so in order to find this, we do the same thing that we did before. We're going to go utilize Desmos. So still working on the normal curve, but this time, instead of it having 97.5% beneath it, it's going to have everything except that 0.5%. So this is going to have 99.5%. Oops, of all of those values beneath it. So that's going to correspond to a z-score of about 2.58. So this is going to give us about 2.58. And these z-scores that we're working with, the 1.96, 2.58, these are all common z-scores that you'll see and you'll encounter when we do confidence intervals, at least with the z-scores. Okay. So what we have here is we have the same mean, same standard deviation, so it's just 2 plus or minus 2.58 times 0.1. So our confidence interval is between 1.742 and 2.258. So let's interpret this statement. So this tells us we are 99% confident the mean number of songs downloaded is between 1.742 and 2.258. All right. So, interesting thing to notice here. Notice that as our confidence level went up from 95% to 99%, the range also went up, right? The interval got larger. And so that what that's telling us is the interval is more encompassing. It includes more values, so it gives us a better chance of being accurate, right? Because if I said, well, back up at this example, say, well, that's well and good, but maybe I'm not comfortable being only 95% confident, right? Maybe that 5% chance that I'm wrong is not sitting well. Maybe I want to be 99% confident in my answer. I say, okay, well, in order to do that, instead of it being from 1.8 to 2.19, it's going to have to be 1.7 to 2.25, something like that. And we would say with a 99% certainty that the value must lie somewhere between these two. Okay? So this is what we mean when we're talking about a confidence interval, is how confident are we that a value, in this case a mean, lies within a particular range or a particular interval. Okay. So let's look at section 8.2. So we've already talked a little bit about the point estimate. But the point estimate of the population for the mean is the sample mean. Okay. So let's look at this example here. So pennies minted after 1982 are made from 97.5% zinc and 2.5% copper. The following data represent weights in grams of 17 randomly selected pennies minted after 1982. Treat the data as a simple random sample. Estimate the population mean weight of pennies minted after 1982. So what it's asking for here is for us to estimate the population mean weight of pennies. Okay, so when it says estimate, right, we're using, again, our point estimate here. That's our sample mean. So it's really saying find x bar. So to do that, we would do 2.46 plus 2.47 plus etc., etc., etc. Right, because this is just all calculator work basically, and all the way through the list down to 2.45 divided by the total number, which is 17 terms. This is approximately 2.464. Okay, so that's our x bar. That's our point estimate, okay, our sample mean. Now, we're going to look at something a little bit different. This is the t distribution. Okay, so suppose that a simple random sample of size n is taken from a population. If the population from which the sample is drawn follows a normal distribution, the distribution of t follows the student's t distribution with n-1 degrees of freedom, where x bar is the sample mean and s is the sample standard deviation. So basically, what this t distribution is doing for us, the t distribution allows us to work with a normal distribution that primarily deals with samples. So sample mean and sample standard deviation. Okay, so oftentimes when you're actually running tests in statistics and you're testing different values and finding confidence intervals with any particular value, we're going to be using t. We're going to use the t distribution instead of z-scores, because the t distribution works with samples rather than with entire populations. Now the degrees of freedom, so n minus 1 degrees of freedom, that's just one less than the sample size. This can change what the graph looks like. So if you notice down here at the bottom, we have a bunch of different versions of this graph. That's because as the degrees of freedom increase, so as degrees of freedom increase, okay, then we end up getting a much taller graph. So you end up getting the graph is taller and thinner. And basically it's less spread out this way. Because as the degrees of freedom increase, so as our sample size increases, that's going to give us less variability, because the picture is going to become a little more clear about what the actual values are doing. Okay, so here's the properties formally stated for a t distribution. So the t distribution is different for different degrees of freedom. Okay, it's centered at 0 and symmetric about 0, so just like a normal curve. The area under the curve is 1, just like it was before. And then we have, right, half of the area to the left of 0, half of the area to the right of 0. It's asymptotic, so it never actually hits the x-axis. The area in the tails is a little greater than the area in the tails of the standard normal distribution, because we're using an estimate. Okay, we're using the t statistic instead of z. And as the sample size increases, we get closer to the standard normal density curve. So to find t values in the normal curve, so like t sub alpha, so t sub alpha, it's still giving us the same thing that it was before, just now using t instead of z. And we can find this on Desmos. Desmos actually has a feature for this. So let's look at an example. Find the t value such that the area under the t distribution to the right of the t value is 0.2, assuming 10 degrees of freedom. So that is, find t sub 0.20. Whoops. 0.20. That's this area here, assuming that our degrees of freedom is 10. Okay. So to find this, so t sub 0.20, we need to look at Desmos. Okay, get rid of the normal curve there. Go under Functions, under the Distribution tab, and you'll notice right next to Normal Distribution there's this t-dist button, and that is a t distribution, and all Desmos needs now is the degrees of freedom. So in this case our degrees of freedom is 10. So there we go. We have our t distribution with 10 degrees of freedom. Now if we want to get the cumulative probability, well, we need the probability, the area to the right of t sub 0.20. Now again, we can still do dot inverse CDF, but remember, so you've got to be very clear on this, the inverse CDF function only works with area to the left. Okay, inverse CDF function only works with area to the left, but the alpha value is to the right. So don't put in inverse CDF of 0.20, because that's just going to give you an area of 0.20 to the left. If the area to the right is 0.20, that's what the alpha is, then the area to the left must be everything else, or 0.80. Okay, so it's 0.80, not 0.20. All right, and that gives us a value of approximately 0.879. So 0.879. All right. So we're still reading these curves the same way we read the standard normal curve. So when it comes to constructing a confidence interval for the population mean, so we're looking at confidence of 1 minus alpha times 100%. So a few conditions have to be met. The data has to come from a simple random sample or a randomized experiment. Sample size is small relative to population size. And then the data come from a population that is normally distributed, or the sample size is large. Because if the sample size is large enough, then those sample means will be normally distributed regardless. Okay. So to find the upper and lower bounds, so that's right here. So the formula is very similar to what we saw on the previous page. So you take the x bar value and you take plus or minus t sub alpha over 2 and then times s over the square root of n. All right, so that's standard deviation for x bar. Okay. So let's look back at the penny example. So construct a 99% confidence interval about the population mean weight of a penny. So let's remember what we know here. So just put it up out of the way. So we know that x bar we found on the previous page. So x bar was 2.464. We know that n is 17, right? We had a sample size of 17 pennies. S, our standard deviation for the sample. If you calculate that just on Desmos, that's 0.0177. And our degrees of freedom, if I can get that on here. So our degrees of freedom is going to be 17 minus 1, so 16. So our t-score is going to be t sub 0.01 over 2. All right, that's our alpha over 2. So it's t sub 0.005. Okay, if we find this on Desmos, okay, we do tdist. This time our degrees of freedom is 16. And we're trying to find everything to the left, so that was going to be 0.995. Oops. Only one decimal place, 995. There we go. So we have about 2.92. So this is 2.92. So for our confidence interval, we're looking at 2.464 plus or minus 2.92 times 0.0177 over square root of 17. Okay, and if we go ahead and just run this through Desmos, through calculator or something, we have our 99% confidence interval. That's going to be from 2.451 up to 2.477. Okay. So again, remember what this tells us. This says that we are 99% confident that the mean weight of a penny, so of the population of pennies, must be, we're 99% confident that it is between 2.451 and 2.477 grams. Okay, so that's what this statement is telling us. Okay. So now let's look at that next example down here at the bottom. The effectiveness of a blood pressure drug is being investigated. An experimenter finds that on average the reduction of systolic blood pressure is 22.1 millimeters of mercury for a sample size 788 with a standard deviation 20.8. How much of this millimeters of mercury will lower for a typical patient's systolic blood pressure after taking the drug? Estimate with 90% confidence. So let's look at what we've been given. So we know that on average the blood pressure is reduced 22.1. So that means X bar is 22.1. Sample size is 788. So N is 788. And standard deviation of 20.8. So S is 20.8. And our degrees of freedom is just 788 minus 1, so that's 787. Okay, so very high number of degrees of freedom here. So our T sub alpha value, so we're constructing with 90% confidence, so that means alpha is the remaining 10%. So that's T sub 0.10 over 2. So that's, so that's T sub 0.05. Okay. With 787 degrees of freedom, so let's find that. So we have 787 degrees of freedom, and we're looking at the area to the left being 0.95, right, because the alpha over 2 value is 0.05. So that would give us a t-score of 1.65 approximately. So 1.65. So our confidence interval, so we get 22.1 plus or minus 1.65 times 20.8 over the square root of 788. So our 90% confidence interval is going to be from 20.877 to 23.323. Okay, so we are 90% confident that the mean reduction in systolic blood pressure is between 20.877 and 23.323 millimeters of mercury. Okay, so that's what that confidence interval is giving to us. All right. So now find the sample size needed to estimate the population mean within a specified margin of error. So this one's actually pretty interesting because this is telling us that, say I'm going to conduct an experiment, and I want to have a certain level of confidence, but I'm not sure how many people I need to survey, to interview, in order to get that level of confidence. Say, I want to be 95% confident, right? Or I want to be 99% confident in my interval. How many people do I have to talk to before I can get that level of confidence? And we actually have a formula for that. So it's this formula right here. Okay, so this is going to be n equals z sub alpha over 2 times s, so that's our z-score, times the standard deviation over the margin of error e, and it's that value squared, and then n is rounded up to the nearest whole number because you can't have a fraction of a person. Okay. So let's look at this example. So again, to the pennies. So how large of a sample would be required to estimate the mean weight of a penny manufactured within 0.005 grams with 99% confidence? And assume s equals 0.02. So they're rounding our standard deviation for us. So we're trying to find how many people, or how many pennies in this case, we need to evaluate in order to have 99% confidence. So that means in the tails here, that remaining 1% has to get split, so that's 0.005 in each tail. Okay. So our z-score, z sub 0.01 over 2, that's z sub 0.05. This value is 2.58. And we found that one earlier. You can go back and look at that. So, in order to get this accurate with 99% confidence, we need to interview n equal, or we need to sample, I guess, how many pennies. N equals 2.58 times 0.02 over the error 0.005, because we want to be within 0.005 grams of that weight squared. This gives us approximately 106.5, but of course we need to round this up to the nearest whole number. So we have 107 pennies. So again, what this is telling us is if you want to be 99% confident that the mean weight of a penny is within this many grams of a particular value, then we need to check at least 107 pennies and their weights in order to determine that value. Okay. So now, let's look at section 8.3, so a population proportion. So we're going to be doing something very similar to what we did in the last section, so we're still finding confidence intervals, but this time for that proportion. We saw this back at the end of the last chapter as well. So remember the sample proportion p hat? Well, p hat is going to be our point estimate for the population proportion. Okay, so that point estimate, that approximation, that guess value coming from a sample. And we compute this with x over n. Okay, so just as a reminder, in this example, this poll asked 1,783 registered voters nationwide whether they favored or opposed the death penalty for persons convicted of murder. Of those registered voters, 1,123 were in favor. Obtain a point estimate for the proportion of registered voters nationwide who are in favor of the death penalty for persons convicted of murder. So our point estimate, that's p hat, is going to be 1,123 in favor out of total 1,783 voters that were interviewed, which is approximately 0.63 when rounded to 2 decimal places like they wanted. Okay. So hold on to this because we will be coming back to it in a little bit. Now for a confidence interval for a population proportion. So in this case, we're doing things very similarly to how we did before. So the mean is p, right? The standard deviation uses that same formula. But now for our lower and upper bounds, okay, given our confidence interval of 1 minus alpha times 100%, the lower bound and upper bound come from p hat plus or minus z sub alpha over 2 times that sigma value, right? That sigma sub p hat. Okay, so it's the proportion plus or minus z-score times standard deviation. Okay, so let's go ahead and take a look at an example. So this is following along with the same example with that poll. Okay. So we're going to have here p hat, so hold on to that formula. So that's going to be 0.63 plus or minus, so 90% confidence, so that's alpha is 0.10, right, so 10%. So alpha over 2 is 0.05, right, 5%, times square root of p hat, which is 0.63, times 1 minus p hat, so that's going to be 0.37, over n, which is 1,783. The z-score at 0.05, that's going to be 1.65. So let me just go ahead and put that in right here. So that's going to be 1.65. Okay. So 1.65 right there. And then that gives us our confidence interval. So 90% confidence interval from 0.611 to 0.649. Okay. So again, let's interpret this. So what is this confidence interval telling us? Well, so this tells us that we are 90% confident that the proportion of voters in favor is between 0.611 and 0.649. So, in other words, we don't know with certainty, right? We don't know what percentage of the whole population of registered voters actually do support this idea, but we know what our sample thinks, and now using just that sample, we can determine how accurate we think that sample is. So we say, okay, well, how confident are we that the actual entire population proportion is within this interval? We're 90% confident. Okay, so I'm 90% confident that the proportion of voters in favor for this measure is between 61% and 65%, basically. Okay. So let's look at another one. In a survey funded by the University of Washington School of Medicine, 750 of 1,000 adult Seattle residents said they did not believe they could come down with a sexually transmitted infection, or STI. Construct a 95% confidence interval estimating the proportion of adult Seattle residents that do not believe they can contract an STI. Okay, so first we need to get that point estimate, so that p-hat value. So that's going to be 750 out of 1,000. Okay, so that's just going to be 0.75. So our value, so that's going to be 0.75 plus or minus, now 95% confidence, so alpha is 5%, so 0.05. Half of that is 0.025 times square root of p-hat times 1 minus p-hat over n, so over 1,000. Okay, z sub 0.025, right? If we go find that corresponding z-score, we've seen this one before. This is about 1.96. Okay, and then we can just kind of plug and chug these numbers. So we got 95% confidence interval is between 0.723 and 0.777. Okay, and then it wants us to round that to 2 decimal places, so let me do that. Just do that, and then that one becomes 0.78. Okay. So then the interpretation that we're left with says we are 95% confident that the proportion of Seattle residents who believe this is between 0.72 and 0.78. Okay, so we are 95% confident that the proportion of Seattle residents who believe this is somewhere between 72 and 78% for the entire population, not just for our sample, because our sample we got was 75%. Okay. And then for this last page, so similarly to what we did in the last section, we can find how large our sample size has to be in order for us to have a particular margin of error and a particular level of confidence. So in order to do this, we're going to use this formula. Okay, so it's similarly designed to the previous one. There's just one extra little caveat here, because in order to find the value for p-hat, we need to know what n is, right? Because remember, our formula for p-hat is x over n. So how in the world am I supposed to find n using p-hat if I need n to figure out what p-hat is in the first place? Well, we have 2 ways that we can overcome that. So we can use an estimate of p-hat from a previous study. Okay, so if somebody else previously studied this situation, this phenomena, then we can look at their study, use their p-hat value, and then start comparing against that. Or we can let p-hat equal 0.5. And this is going to give the largest possible value of n. Okay, so largest possible value of n. Because I would rather interview too many people, right? I would rather have too big of a sample than too small of a sample. Because if the sample's too small, it doesn't give me good data. Okay. So let's look at this example. So a sociologist wanted to determine the percentage of residents in America that only speak English at home. What size sample should be obtained if the sociologist wishes that the estimate is within 3 percentage points with 90% confidence, assuming that they are using the estimate obtained from the Census 2000 supplementary survey of 82.4%. Okay, so the first key here is they're using the estimate of 82.4%. So that tells us p hat is 0.824. Okay, so in this case we are using a previous study's value of p hat. So then our n value, so n, is going to be p hat times 1 minus p hat, so that's 0.176 times the z-score, which we've found before, it's 1.65, over the margin of error, which we want to be 3 percentage points, so that's 0.03 squared. Plug and chug this on your calculator, it's going to give you 438.7, and then round that up to the next whole value. That's going to be 439 people, okay, in our sample. Okay. So that would be the required sample size in order to get 90% confidence that the actual proportion in the population is within 3 percentage points of what we get. Okay. So that is the end of chapter 8. Okay, so that's going to be it for us for this chapter, for this lecture. So I'll be talking with you all soon. We're going to do a little bit of review leading up to that exam. And that's it for confidence intervals for the time being. So if you have any questions, let me know. Be sure to take a look at the homework for that as